Now we look at the annihilator. So for a subset U of a vector space V, the annihilator of U is U naught, so superscript 0 here, and this is all the elements of the dual space that can kill everything in U. And so that means in particular that U is in the null space of phi. So you can see that this is all of the phis in V that contain U in their null space. Okay, so let's see. So we have quick proposition, and that is that the annihilator is a subspace. And the proof for that one is so straightforward, I'm going to skip it. You can take a look in the book if you like. And then let's talk a little bit about the annihilator in the context of contravariance. So suppose we have U as contained in W, contained in some vector space V, right? So then if if we look at something from the annihilator of W, so that phi of W is equal to 0 for all W and W. So in other words, here we're taking phi to be something from W naught. Then you can see that phi of U is going to be, well, if U is contained in W, then it's going to be 0. Right? And so that tells us then that phi is in the annihilator of U as well. So we just showed that W naught is contained in U naught. So we've reversed this containment by passing to the annihilator. And in fact, this goes both ways here, so that U is contained in W if and only if the container of omega, the annihilator of omega is contained in the annihilator of U. What else do we have? So other fun facts. Suppose we take U to be the trivial subspace. What happens when we take the annihilator of this guy? Well, if I'm looking for the annihilator, that's going to be, I'm asking the question, which functionals phi send U to 0? And the answer is, well, they all do. So any functional does that. And so this is actually an if and only if as well. If the annihilator of U is all of V prime, then that means that U has to be trivial. And I could do it the other way around and say, okay, well, let's take the opposite extreme. What if U is actually all of V? And I want to find out what the annihilator of U is. All right, well, now the question that I'm asking is, which phi send all of V to 0. And the only guy strong enough to do that is the 0 functional. And this is also an if and only if. So you can see that if I take the minimal subspace on one side, then the annihilator gives me the maximal subspace. And if I take the maximal subspace on the first side, then the annihilator gives me the minimal one. So here's more of the contravariance of duality shining through. Let's see, so here's another example of that. So now, if U and W are any subspaces, and so what I mean by any here is I'm no longer assuming that that U is contained in W like I was above. But if we just have any subspaces, then let's see. If I look at the sum of U and W, and I want to take its annihilator, then let's see. So anything in the annihilator has to be strong enough to kill all of U and kill all of W. So if it kills all of U, it's in here, and if it kills all of W, it's in here, and it has to be in both. Well, if it's in both, then there's an and. That means we've got an intersection, and so this is in fact equal. Similarly, if we look at the intersection of U and W, and we take its annihilator, then let's see. So, well, if you've got something that's strong enough to kill U, no pun intended, then since the intersection is a subset of each of its component sets, right? So this is a subset of U. So that means that if I kill U, or I kill W, then that's good enough to kill anything in the intersection. All right, and so I haven't made any of this precise. If you want to make any of this precise right here, this is all exercises 17 through 23 for this section. Okay. But the arguments for it are essentially the ones I just talked you through. So now we have proposition 106. And so this is if we've got a finite dimensional vector space, then with a subspace U, then the dimension of U plus the dimension of the annihilator of U gives you the dimension of the whole space. And this is very intimately related to the rank nullity theorem. Okay, so let's see. For the proof of this, let's consider the inclusion map. Oh, by the way, sometimes people do the inclusion map with a little curly, a hook arrow like that instead of the inclusion symbol. So you can use whichever one you like. So I of U is equal to U. So we saw that I prime is the restriction map. And we also saw that the restriction map is surjective because any function can be extended to be, any functional can be extended to be linear on the whole space. So recall that the range of I prime then is going to be all of U prime, since it's surjective. So the rank of I prime is the dimension of u prime, but the dimension of u prime is the dimension of u, and that was by proposition 395, that a space and its dual have the same dimension. Okay, so that gives us part of it. And now we also have, let's see, so if we take something from the, let's look at the null space. So if we look at something from the null space of I prime, phi is in the null space of I prime if and only if we have, let's see, I prime of phi applied to u is equal to 0 for all u. And let's unpack a little bit of what this is. So this is phi of I of u, which by the definition of I is phi of u. And so recall, since we're in the null space of I prime, the guy on the left has to be equal to 0 for all u. And that tells you that phi of u is equal to 0 for all u. And that's exactly what it means to be in the annihilator of u. Right? So we just discovered that the annihilator of u is the null space of I prime. And then putting this all together with rank nullity, we have that the dimension of v prime is the dimension of the rank of I prime plus the dimension of the null space of I prime. And we worked out that the dimension of the rank of I prime was the dimension of u, and that the dimension of the null space of I prime is the dimension of u naught, because in fact they are the same. And that's what we wanted to show. Oh, and I guess on the left side, the dimension of v prime is the dimension of v, by, again, what is that, 395. The end.